Hello everyone, and welcome to the M2L31 Level 1 training course. Today, we will introduce a peripheral in the low power domain of the M2L31 series, the Low Power ADC. Within the low power domain, multiple energy-saving modules, such as low power PDMA, low power GPIO, low power ADC, low power I2C, low power SPI, low power UART, and low power timer, are integrated and controlled by the low power digital logic. This allows them to continue operating even when the main system is in sleep mode. In this session, we will focus on the low power ADC, which is responsible for analog to digital conversion. Before diving into the low power ADC, let's understand the differences between low power ADC and EADC. In the M2L31 series, the low power ADC and EADC share the same analog circuitry, which means they cannot operate simultaneously. You must choose one or the other in your design. The main differences lie in the maximum sampling rate and the auto operation mode. The low power ADC has a sampling rate of 571 kilosamples per second, which is lower than the EADC's 3.42 megasamples per second. However, the extended sampling time of low power ADC can go up to 16,383, compared to 255 for EADC, making it more suitable for high impedance inputs. Additionally, the low power ADC supports auto operation mode, allowing automatic data transfer through the low power PDMA during power down mode, enabling continuous low power ADC operation. In the M2L31 series, the low power ADC offers 4 selectable clock sources: PCLK2, LXT, MIRC, and HIRC. By using the LPADC0DIV prescaler register, you can configure and adjust the actual operating clock of the low power ADC. With a 12 MHz clock, the ADC can achieve a maximum sampling rate of up to 571 kilosamples per second. This slide shows the complete block diagram of the low power ADC. Once the system voltage is stable, the ADC can be controlled sequentially from digital 0 to 3. From the block diagram, you can see that the first step is to select the ADC trigger source, such as software trigger, EPWM trigger, PWM trigger, or timer trigger. Once triggered, the ADC will use the analog multiplexer to connect the selected input channel and perform charging and discharging on the internal ADC capacitor. The signal is then converted and processed by the ADC macro, and the result is stored in the corresponding channel data register. Finally, an ADC interrupt is generated to notify the user that the conversion is complete. When selecting ADC input channels, the low power ADC offers 3 operation modes. Single mode. One trigger performs a single ADC conversion, producing data for one input channel. Single cycle mode. One trigger performs ADC conversions for the specified channels in one cycle, producing data for multiple input channels. Continuous mode. One trigger allows the ADC to continuously convert the specified channel until the program stops the ADC. These modes give flexibility depending on whether you need single-shot, multi-channel, or continuous sampling. If the ADC conversion speed is too fast or the load is too light, it may result in inaccurate ADC results. This is usually caused by insufficient charging and discharging time of the internal ADC capacitor. To address this, you can use the extended sampling time feature to increase the sampling duration and ensure accurate conversion. The EXTSMPT register allows users to adjust the sampling time. It is generally recommended to set it to at least 10 times the RC time to guarantee correct ADC conversion values. To improve ADC accuracy and internal parameter matching, the ADC must perform internal calibration each time the system powers up, and AVDD and the reference voltages are stable. In calibration mode, the system measures and corrects offsets and mismatch errors. During normal operation, the ADC automatically applies the compensation results. However, these calibration data are lost when the power is turned off. so the calibration must be performed again each time the system powers up. The ADC supports compare mode, which functions similarly to an analog comparator. This feature uses two sets of comparison registers, ADC MPR0 and ADC MPR1, where you can configure the comparison channel, which is CMPCH, the comparison value, which is CMPD, the comparison condition, which is CMPCOND, the number of consecutive matches, which is CMPCNT. When the ADC measurement of the specified channel meets the comparison condition for n consecutive times, the system will trigger an interrupt. This functionality is useful for applications such as overvoltage and overcurrent detection. Auto operation mode is a key feature of the Low Power ADC. It allows the ADC to start automatic operation using various trigger sources such as low power timer, tick timer, WKIO, or ACMP. When Auto EN is enabled, the Low Power ADC can perform ADC conversions even when the chip is in low power modes, which is NPD0 to NPD4. By pairing with the Low Power PDMA, ADC data can be automatically transferred to Low Power SRAM, storing each conversion result. The Low Power PDMA can then generate CPU wake-up events. This process requires no CPU intervention, reducing wake-ups and achieving ultra-low power operation. That concludes our training session on the Low Power ADC. We also have video demonstrations using example programs, which you can find in the video list. Thank you for watching, and if you'd like to learn more, please feel free to contact us.